So the term Cellular V2x has been a term that I've been hearing a lot during the last couple of years, probably because it was my research domain or because it was a pretty trending technology recently competing with DSRC. So let's spend a minute and see what it's exactly about. So probably we are all familiar with the connected vehicle technologies. And two main solutions so far proposed by IEEE and 3GPP communities are IEEE 8211P, also known as DSRC, and Cellular V2x proposed by 3GPP Release 14. And my work is mostly focused on the latter, which is the Cellular V2x, or also known as CV2x. You might have heard it as LTEV, LTE-V2V, or other technologies, but basically I think we are all talking about Mode 4 Release 14 3GPP standard. So unfortunately I have another paper which is going to be presented tomorrow. The paper I'm presenting today is a continuation of that one. So it's a bit tricky. I'm going to try to give you all prerequisite information that's related to understand this work. But if you're really interested in the domain, I would suggest also attend that session because that will be a deep dive into the topic. So let's see what's the problem I'm looking at this moment. Think of a setup like what we have in the picture. A super congested highway with potentially thousands of vehicles in it. And every vehicle is transmitting a basic safety message at the rate of 10 Hertz, so every 100 milliseconds. That's a huge load on the network, considering that we only have 10 megahertz of bandwidth. So the problem we are facing here is simply network congestion. And the solutions proposed for this problem for DSRC a couple of years ago was basically the SAE J2945/1 standard, which proposed some kind of a congestion control solution to address this problem. And similar effort is also going on as SAE J3161. I think the meetings are ongoing right now. I'm not sure if Dr. Lansford from Qualcomm is going to attend this conference or not, but probably he's the best person to ask about this, because I think he's leading the efforts in that domain. So the work we did in both of papers, the one that I'm presenting today and the other one that's going to be presented tomorrow, is answering the question that how a congestion control enabled CV2x can be realized. Basically, how can we use the background from J2945/1 and port it into the 3GPP requirements? Because these are two very different standards. And basically the congestion control in J2945 is defined for DSRC. It's not necessarily working very well for CV2x, or it might, but basically this is the question we are looking at. If we borrow the design rationale from the SAE standard and make it to work on the 3GPP standard, what's going to be the result? So in order to look at this problem, first, very briefly, let's look at what's the nature of CV2x. How does CV2x works in terms of MAC layer and resource allocation procedures? The resource allocation scheme in CV2x is mostly known as the sensing-based, semi-persistent scheduling, or so known as SPSPS. And if you're interested in the details of this procedure, I would extremely suggest reading. There's a very nice paper from Dr. Gonsalves in VTM. That's basically how I started working on this domain. And I also had another paper last year at VNC, which goes very deep into the details of only resource allocation and MAC layer performance of CV2x. But I'm just going to show you a very brief understanding of how it works. So basically, the Sps algorithm is mainly based on two concepts. One is sensing the previous history of the network and keeping basically a history of which packets have been transmitted by other nodes and which resources. So we keep a history, which here I'm calling it as the sensing window. And then we use them to kind of make sure that we are not colliding with the UEs that are close to us. So let's say a node is hundreds of meters far from me. If I also rewrite my message on the same radio resource that node is transmitting on, there will be a collision between us. But it's not really of a big deal because we are already too far from each other. What I'm really trying to achieve is to avoid collision between nodes that are close to each other. In other sense, try to not allocate my message on a resource that has a high received power level. So that's basically how it works. I keep the track of all received messages, measure the power in those, and if required, I remove them. And the second rationale or the second concept is to do what I said in a semi-persistent manner. So every UE or every user equipment has a counter. It's a random counter, and I basically randomly change my resource allocation. And everybody, I mean, it's a distributed fashion, right? Nobody knows about each other. So I keep changing my resource in a semi-persistent manner. And basically the two papers I mentioned, my old paper and Dr. Gosalves, the paper from Dr. Gosalves showed that actually it works pretty well, even in very highly congested scenarios. So in this work, we're assuming that SPS is doing its job. But what will happen if I put the SAE J2945 standard on top of it? How they're going to work together, and what's going to be the result? So this is basically the problem we're looking at. For those of you who are not familiar with this standard, basically the congestion control defined inside the SAE standard provides two algorithms. First one is the rate control, and the second one is the range control or power control. And basically what we call them after porting them into the 3GPP requirements is a DCC-enabled CV2X. DCC stands for Distributed Congestion Control. So after this, I'm just gonna refer to it as DCC-enabled scheme. So let's jump into some results and basically show you what are the observations we have done. In this paper, I'm looking into 4 traffic scenarios, all of which are pretty high density, but in one, we are looking at a stretch of 3.6 kilometer road with 12 lanes, which is basically a generic highway in the US. And I start with 600 vehicles in the highway and go all the way to 2,400 vehicles, which is a pretty dense scenario. It's almost like a parking condition that vehicles are basically very close to each other. And so this is the least dense one, which is, I might call it low density scenario, but our low density scenario is also pretty congested and pretty dense. So as you can see here, we almost see no difference between two curves. The curve on the right hand side refers to the DCC enabled one, and the left hand side is basically the base CV2X. We see almost no difference. They are almost identical. And the reason, as we will see in the next slide, is DCC hasn't kicked in yet because the density is so low that congestion control doesn't even get activated. But if you go into higher density, which I call it freeway low density and has 1,200 nodes in it, we'll see that there are minor differences. So the important point, and something I would like to mention, is if you look at here, we have, basically, let me give you first a view of what is this plot about. We are looking at the distribution of messages each in radio resource. So basically here I'm saying that there are a bunch of resources that have 0 message in it, which means they're unutilized, which is something we don't like, right? We want to use all of our radio resources, and ideally I don't want to have any radio resource with 0 messages in them. I also have a bunch of radio resources with 1 or 2 messages in them. So here the important thing that's happening is, you see, in the base CV2X, which doesn't have congestion control, you have a bunch of resources that have 0 message in it, meaning they're unutilized. But what congestion control does is, after applying congestion control, you see here we also we have more number of unutilized ones. So this is actually a warning to us that congestion control is somehow interfering with the Sps algorithm, because the resource allocation ideally, as a general statement, tries to make sure that we are fully utilizing our channel, so we don't have any unutilized resources, which is what's happening in the left-hand side plot. But after applying congestion control, looks like now we have a bunch of unutilized resources. So this is something to keep in mind, and we're going to talk about it more. Going into higher densities, we see that the distribution is shifted to left, meaning that we have less number of resources with high collision. So here you see we have a bunch of resources that have 10 packets or 12 packets into them. And that's basically, we can say that almost all of the messages in that resource are basically lost. And we wouldn't want to have anything on the right-hand side of this plot. We want to stick to the left and have, like, ideally many resources with one message and a couple of resources with two messages and so far. And basically, in this sense, congestion control is shifting our distribution to the left, which is what we're expecting from congestion control. But also pay attention, what I mentioned before is we also get some unutilized radio resources. And going into very high densities, basically it's so obvious that congestion control is helping us with doing its job. Here on the base CV2X, we have very, very heavy collisions. So we have resources that are allocated that have 16 or 14 messages inside them. That means that we're losing a lot of packets. But after activating the congestion control, you can see that again distribution is shifted to the left, and the number of messages in each radio resource or radio block or RB is basically much lower. So let's look how basically these are all simulation results, right? Let's see from the moment that I run the simulation, how does the system behave? What's the temporal behavior of the system? So this is something interesting. Basically from top to bottom, it's low density, 600 nodes, all the way to 4,800 nodes in the bottom scenario, which is pretty high density. So looking at the first plot, the x-axis here is showing the time, basically the simulation time. From the moment that I trigger the simulation, if you look at this area, basically the number of UEs that are unutilized, very light blue, are decreasing. Meaning that when I run the simulation after a while, resource allocation or SPS does its job and reduces the number of unutilized resources. And this is something interesting because we would expect to see that, right? If we start the simulation from time 0 and I see no change in the number of unutilized RBs or radio resources, that means that my resource allocation is not doing a good job in distributing the messages throughout my resources or throughout my communication channel. And also the same thing happens in the congestion control. As I mentioned before, the congestion control hasn't kicked in yet, so basically left and right hand side plots are almost identical. Let's look at the second plot, which is pretty interesting. So something else is happening around like 5-second time. You can see that we have like an upslope here. So basically this is congestion control working. And how do we know that? Is first of all, by comparing left-hand side and right-hand side plots, and second, I'm going to show you how congestion control parameters are changing with time. Then you will see that there is a very good correlation between how our message rate changes and how here this curve is basically showing us the distribution of resources. I'm going to jump to the next slide and come back here. So basically, this is the time behavior of my congestion control parameters. Again, as a reminder, my congestion control parameters were rate and power, which basically governs range. So here you can see that in the second scenario, my rate is kind of increasing. My rate is decreasing, meaning that my inter-transmit time is increasing. So just look at this trend, and I'm going to go back to the slide before. You can see that it's almost identical to what we have here, right? You can see basically the rate decreases, and hence the distribution of messages in the RB changes in the same manner. It's a very good correlation between rate and what we see here. But we have also a second algorithm, which is power. Let's see what power is doing. So initiating the simulation at time 0, power senses a very high channel busy percentage, or CBP, because the channel is pretty utilized. And it drops down to its minimum possible value, which is 10 dBm here. So you can see that the power drops down to 10 dBm, but the CBP here, the left-hand side plot, doesn't make, we don't see a huge change here. So what's the conclusion here? It's a very important observation. Our power goes down, our CBP is not changing. So what was the responsibility of power control? To bring down the channel busy percentage. We are overutilizing our channel, there's a congestion, we want to avoid the congestion. But it looks like power control is not doing its job. And what's happening afterwards is rate control kicks in and the rate starts decreasing. Now we see that after rate control kicks in, actually now CBP is going down. And power control senses that and sees that, okay, rate control is doing its job, he's doing the heavy lifting, I don't really need to decrease the power, and the power goes up. So what's the conclusion here? It looks like our power control tries to do something by decreasing the power to minimum possible minimum possible value, but it doesn't work. Rate control kicks in and the power control kind of gives up. This is also a very important observation, which I'm going to talk about it more in the next slide. And the next one is another observation about what's the distribution of the distance between colliding UVs. Why is this important? I would ideally, in a connected vehicle scenario, ideally I would like to have less number of collision between UVs that are close to each other. If two vehicles are separated by 10 meters, I don't want to have them to have a message collision because it's a safety critical scenario. But if UVs that are far from each other, they're basically separated by hundreds of meters, it's kind of okay if their messages collide. So here I look at the distribution of the distance between colliding UVs. And I can see that we have very low number of colliding UVs that are in near distances, and that's also kind of important. That's what we are expecting the SPS to do. But why am I comparing it to the congestion control enabled one? Because as I said, SPS uses the power measurements to kind of estimate the distance, right? But here, our power control is also doing something. It's changing the power, right? So it's kind of fooling the SPS. SPS is going to estimate wrong distances. That's why we're saying that here, kind of the number of colliding UVs kind of increases, which means that power control is kind of interfering with the Sps algorithm. And my last piece of result here, which I'm going to go through very fast, is a question is how rate control. So rate control is also it works in time, right? How does the rate control coexist with SPS? Is the MAC layer able to follow the rate control or not? So basically here, if you look at the blue curve, you can see that it's following the red curve. The red curve is the ITT in the application layer, so our rate at the application layer, and the blue curve is our rate at the physical layer. So it means that whatever application layer says, with 100 millisecond latency, I'm able to follow it in the physical layer. And the last slide is just a visualization I'm going to show you. On the top plot, if you focus on the top plot, the color shows the distance between colliding UVs. So ideally, as I said, we don't want to have colliding UVs with low distance, meaning yellow or red colors. I'm going to reset the animation so you can see that by the time goes forward, the number of basically grids that have very light color decreases. So white and yellow ones kind of decrease when the simulation goes forward. That's basically what SPS is doing, right? If I reset it again, in the beginning we have a bunch of yellow and whites, but when the simulation goes forward, they vanish basically, and basically we don't have colliding UVs that are very close distance. Thank you. I think I'm gonna skip the conclusions.
Okay, thank you very much. Okay, questions? Yes.
I wasn't sure from your slide on power control. Did you do the simulation with and without power control?
Yes, actually I've done a pretty much large set of different scenarios with power only, rate only, power with different parameters. Those are in the first paper, which is going to be presented tomorrow.
Okay, I'll come back.
Yeah, so if you attend that one, I can show you the results with basically 15 scenarios with different congestion control parameters. But as I said, that's kind of prerequisite for this one, so it's kind of tricky that they're displayed.
Can I ask you for a spoiler then?
Definitely.
Is power control necessary for D2V with CVX?
So what's the question?
Do we need power control for CV to X when we're doing V2V?
I think that's still an ongoing discussion. I'm going to avoid answering the question because 3161 committees is still looking at that. And basically, people are trying to come up with better power controls, not necessarily identical to J2945, but maybe something more effective. So probably that's a question for Dr. Lansford, I guess.
John?
Sure.
Yeah, so you actually have a couple of 3161 voters here in the room.
Yeah.
Just a couple of questions on the assumptions in your simulation. So, do I have it right that the traffic is moving toward each other, so cars are encountering oncoming traffic? And when you said 600 to 2400, that's, okay, great. Oh, that's what I want to know. So
12 lanes.
Over 3.6 kilometers, right?
Basically, it's 6 kilometer stretch, but they only extract the middle one to avoid the edge effect.
Okay.
Very similar to the studies that we have with CAM and basically previous years. Basically, it's exact same setup as CAM setup,
Okay.
and basically we needed to change some stuff like definition of CBP, because CBP is defined for DSRC.
Right.
Here we have a totally different OFDMA setup that resources are distributed in both frequency and time,
Right.
while in DSRC you only have time distributions.
Okay. So the 600 is in the 3.6 kilometer.
3,600, yeah, 3,600.
And then last question, when you start using the ITT control in the SPS, what are you doing about reservations? Are you continuing to reserve at 100 milliseconds?
That's also a good question because 3GPP allows you to have like this drop after. There are a couple of parameters that if you keep dropping something, you initiate or you trigger a new resource allocation. We have tried different setups that again are in tomorrow's paper, but basically details of how did we make the congestion control to work with CV2X. Basically, I think all of those questions goes to tomorrow's paper, or we can have an offline discussion if you have time.
Thanks a lot.
Sure.
Yes.
Alright, thank you very much for the presentation. Can you please go back to page 13? Yeah, so if I look at the very bottom right ITT figure, why is that changing gradually? Like it takes almost 10 seconds to settle down. Because my understanding is ITT is determined based on number of vehicles present in your 1 meter's range. And I think that should be a constant number.
That's a very good question. But basically, I'm gonna rephrase your question. How fast our rate control is able to adapt to a change in a scenario? So if I enter a high density scenario at time 0, how long is it gonna take for me to get to that ITT value, which is 600 milliseconds, right?
Yeah.
Or around 500 probably. So basically, if you look at the J2945 definitions, there is one sliding window size, which is not 100 milliseconds. So every time you change your density or number of vehicles around you, which is what triggers rate control, it takes you some time to go and basically stabilize to that number. And that's actually something important because it looks like the current rate control is not able to change very fast. It's not able to adapt to environment changes very fast because of that definition. If you're interested, we can go through the standard and I'll tell you exactly which parameter is doing this.
Does this mean that you have a changing vehicle density within one meter range, or it means that it actually takes you 10 seconds to converge?
It actually takes you 10 seconds because what's happening here at time smaller than 0, you have 0 number of vehicles.
Okay.
Then when you initiate the simulation, suddenly you have a bunch of vehicles.
Right.
So it looks like it's a step function for your number of cars in your neighborhood, right?
Yeah.
And basically that's the time constant your rate control needs to kind of converge to that 500 millisecond value.
Okay.
And that's very important because we don't want that. We don't want that 10 second, right?
Thank you.
Okay, thank you very much for that.